Look at the skies of World War II. The aircraft we now remember as untouchable legends, the machines that won the war, originally rolled off the assembly line as rejects and outright disasters. We're talking about a bomber made out of wood, a fighter plane that couldn't breathe at high altitudes, and a naval aircraft so dangerous it was killing its own pilots before they even saw combat. Historical greatness is rarely born perfect. It is engineered through relentless iteration, resilience, and a stubborn refusal to give up. Take the North American P-51 Mustang. When the British asked for help in 1940, American engineers scrambled to design a brand new prototype to meet wartime demands. They pulled it off in an impossible 102 days. But the early version had a specific physical limitation. The American-built Allison engine ran fine near the ground, but once the plane climbed into the thinner air at higher altitudes, its performance tanked. It choked. In combat, this was a catastrophe. Allied heavy bombers were flying crucial daytime raids deep into Germany and taking frightful losses. Without fighter escorts that could operate at those extreme heights, the bomber crews were exposed. In the fall of 1942, engineers tried a simple mechanical swap. They took the American P-51 airframe and dropped in a British Rolls-Royce Merlin engine. This chart shows the result. While the old engine's power plummeted as altitude increased, the new Merlin engine held steady. The Mustang's top speed jumped to over 400 miles per hour, and the high-altitude drop-off vanished. With lungs that could finally breathe in the stratosphere, the Mustang escorted heavy bombers all the way to Berlin. They destroyed nearly 5,000 enemy aircraft, clearing the skies over Europe. Performance hinges on the weakest link. Isolating and replacing that single component turns a failed design into a legend. Around that same time, a British designer pitched an idea that sounded like a joke, an unarmed bomber constructed entirely out of wood. The military brass was openly skeptical, but metal supplies were strained. To get the plane built, de Havilland bypassed the aviation industry and brought in piano makers, cabinet builders, and furniture manufacturers to craft the aircraft's components. The design relied on a unique plywood sandwich, creating a streamlined shell. Early models in the humid Pacific hit a snag. Builders used milk-derived casein cement, which rotted and attracted termites. Production quickly pivoted to synthetic resin adhesives, creating a waterproof bond stronger than the wood itself. The resulting wooden wonder had a radar signature only 10% the size of comparable metal planes. It was so light it outpaced the enemy's fastest fighters. Relying on unconventional materials and outside experts can solve problems that traditional methods cannot reach. Then there is the Vought F4U Corsair. It was intended to be the U.S. Navy's premier carrier-based fighter, but its initial trials were a disaster. The plane had a massive engine that created violent torque, pulling the aircraft hard to one side. Worse, the long nose forced the pilot to sit far back, destroying forward visibility. Trying to land this beast on a tiny, pitching aircraft carrier deck was often fatal. Early Navy pilots called it the Widowmaker. The Navy ultimately rejected it for carrier service and handed the machines over to the land-based Marines. The Marines didn't redesign the aircraft. They changed how they used it. Operating from dirt airstrips, they avoided the carrier landing problem entirely. They had plenty of runway, and they desperately needed a brawler. Free to focus on aerial combat instead of surviving a landing, Marine pilots thrived. They used the Corsair's sheer speed to bully the agile Japanese Zeros, racking up a staggering 11-to-1 kill ratio. Sometimes a design just needs to be placed in the hands of a different user in a different environment. The Mustang, the Mosquito, and the Corsair. These aircraft transitioned from rejected, flawed ideas to the legends that won the war. Think about the roadblocks in your own work right now, that project you are struggling with, or the prototype that feels like a failure. Flaws provide the raw data required to move forward. Every mistake clarifies exactly what to swap, who to consult, or where to pivot. They are the mandatory baseline for your next iteration.